Welcome to today's explainer. Right this very second, there's a totally invisible, hyper-organized city of memory running inside whatever device you're using to watch this. Whether you're holding a phone, swiping on a tablet, or sitting at a massive desktop rig, there is a tirelessly organized metropolis functioning just beneath the glass. Let's dive right in and discover exactly how it works. Think about your device right now. You've probably got a web browser open, maybe a music player going, a messaging app, plus a dozen background processes running all at once. So, how do dozens of these incredibly complex apps run simultaneously, sharing the exact same physical hardware without crashing into each other's data and causing total chaos? Well, that core mystery is exactly what we're going to unravel today. Here is our mental map for today's journey. First, the memory manager. Second, your program's workspace. Third, the virtual memory illusion. Fourth, solving memory shortages. And finally, number 5, advanced memory magic. Let's kick things off with section 1, the memory manager. So memory management is absolutely the core responsibility of your operating system. It's this fascinating mix of hardware, like your actual CPU, and software instructions, all working together to allocate, protect, and free up memory for your programs. What's really wild here is the continuous invisible dance going on. Your OS is essentially the ultimate overworked office manager, constantly handing out desk space, locking filing cabinets, and clearing out empty rooms so the next program can move in. The crucial thing to understand is what this manager is actually trying to achieve. The OS has to give each program its own isolated memory space, prevent those programs from interfering with one another, maximize efficiency, and ensure that data access is both fast and safe. Balancing that lightning-fast speed with strict, absolute safety, that is for sure the manager's hardest job. Because if a rogue browser tab crashes, there is no way it should take down your video call. That strict isolation is the real magic of memory management. Moving right along to section 2, your program's workspace. Let's zoom in from that macro city view down to a single program. It turns out every single running program gets exactly this layout, structured from high memory addresses down to low ones. Up top, you have the stack for function calls and local variables. Right below that is the heap, used for dynamic allocation. Then we find BSS for uninitialized variables, followed closely by data for the initialized ones. And finally, sitting at the very bottom is the text segment, which contains your compiled program code. Literally everything, from temporary scratchpad math to permanent code, gets its own highly specific floor in this building. Now, let's contrast the two busiest floors in this building, the stack and the heap. This is a perfect example of how memory balances speed and flexibility. The stack is incredibly fast and completely automatic, using a last-in, first-out system. But it has a strictly limited size, which is exactly why you might have heard the dreaded term stack overflow. The heap, on the other hand, gives you slightly slower access, but massive, highly flexible size. The catch? It has to be managed manually by the programmer or by a garbage collector. It's basically the difference between a tiny, lightning-fast sticky note and a massive, sprawling whiteboard that you have to clean all by yourself. Moving all the way down to the foundation, we have that text segment. This is usually locked down as strictly read-only, acting as an absolutely critical security feature against catastrophic software failures. By locking the actual instructions of the program, the system ensures that an app simply cannot, maliciously or even accidentally, overwrite its own code while it's running. Okay, on to section 3, the virtual memory illusion. All right, get ready, because here is the absolute biggest plot twist in modern computer science. Modern programs never access physical RAM directly. Just let that sink in for a second. Every single program running on your device right now genuinely believes it has full, exclusive control over your computer's memory. But in reality, they are essentially living inside a fabricated illusion. So how exactly is this illusion maintained? Meet the MMU, the Memory Management Unit. This is a crucial, dedicated piece of hardware that handles address translation. It instantly maps the fake virtual addresses that your programs are using to the real physical locations on your actual RAM chips. It does this relentless heavy lifting millions of times a second so that every single application remains totally, blissfully unaware of the others. And here is exactly how that translation works behind the scenes. Virtual memory gets chopped up into perfectly uniform blocks called pages. Meanwhile, physical memory, the actual RAM, is divided into equal blocks called frames.
To keep track of it all, the operating system maintains an invisible ledger called a page table. When a program asks for a virtual page, the OS checks the page table and flawlessly slots it into a physical frame. It's just a remarkably elegant system.
Which brings us to Section 4, solving memory shortages. You might be wondering what happens when that physical RAM completely runs out of room during peak hours. Well, if a program asks for data that isn't currently loaded into RAM, it triggers what's called a page fault. Think of this like a high-stakes, split-second rescue mission. Step 1, the CPU instantly pauses the current process. Step 2, the OS makes a mad dash to the slow disk drive to fetch the required page. Step 3, the OS updates the page table with this new physical frame. And Step 4, the CPU resumes execution exactly where it left off. The crazy part? The program never even realizes time was frozen. But there's a real danger zone here, a dreaded state called thrashing. If you have way too many programs open, say you're hoarding 100 active Chrome tabs, and your RAM is completely maxed out, the OS starts frantically swapping inactive pages out to the disk just to make room. Thrashing is that critical performance collapse, where your overburdened system is spending more time desperately juggling data back and forth than executing actual program logic. That's when your computer completely chokes and your mouse literally stops moving across the screen. Another massive hurdle the OS has to jump is fragmentation. There's internal fragmentation, which is basically wasted, unused space trapped inside an already allocated memory block. Then we have external fragmentation, where free memory gets scattered in tiny, practically unusable chunks all over the system. Remember our paging system? Paging brilliantly solves external fragmentation by using fixed-sized blocks. It's exactly like packing perfectly standardized moving boxes into a truck instead of awkwardly trying to cram weirdly shaped furniture together. Let's wrap things up with Section 5, Advanced Memory Magic. To keep everything feeling incredibly instantaneous, the OS relies on the modern memory hierarchy. And wow, the speed differences here are stark. At the very top, you have CPU registers, the absolute fastest layer, holding immediate execution data. Next is the CPU cache, which is extremely fast for frequently accessed instructions. Dropping down, we have physical RAM, which is fast, holding our active workspaces. And finally, way at the bottom is the disk drive, the absolute slowest layer, used for long-term permanent storage. The whole goal of memory management is desperately trying to keep your active data as high up on this hierarchy as physically possible. And to squeeze every single ounce of performance out of that hardware, operating systems use practically magical tricks. There's copy on write, where processes safely share the exact same memory space until one of them tries to modify it, which saves massive amounts of space. There's memory mapping, mapping files directly into memory for lightning-fast access. And NUMA, which actually optimizes access times based on exactly where a physical CPU is located on the motherboard. The OS is practically cheating time and space for maximum efficiency here. Actually, it's not just the OS doing the heavy lifting. The software itself helps out too. High-level programming languages like Python and Java bring their own automatic cleanup crews, known as garbage collection. This automatically detects and frees unused memory on the heap, so developers don't have to manually sweep up their own memory messes anymore. It uses clever techniques like reference counting, literally tracking how many times data is linked, and mark-and-sweep algorithms to systematically hunt down and clean up isolated chunks of forgotten memory. So, as we pull all these pieces together, just think of memory management like this. The stack is your fast, short-term workspace. The heap is your sprawling, flexible storage. Virtual memory is the grand illusion layer. Paging is the highly structured organization system making the illusion work. And the OS? Well, the OS is the tireless manager orchestrating absolutely everything from behind the curtain. As we finish up today's explainer, I want to leave you with this one thought to ponder. Since you started watching this, how many millions of invisible page faults just happened right under your fingertips? It's genuinely staggering to marvel at the sheer unseen complexity executing flawlessly on your device, translating virtual illusions into visible reality millions of times every single second.